All right. Let me know if you're able to see the board. Are you able to see the board? Hello? Let me know if you're able to see the board. Hello? You guys are unable to get me? Yeah, so I was asking, are you able to see the board? All right. So circular motion, first of all, just from the weights, from the context of it, circular motion, it involves something moving in or around a circle, along a circular path. Okay? So that's the way we're going to imagine circular motion. Okay. It starts from something simple like a ball. Okay. So when you have a ball, it can all start from the pitch. Somebody hits the ball, what and what. Just that the way the ball is moving, that is also an illustration of rotational motion. From that, we can also talk about a car moving along the roundabout. So when it's moving, making a turn on the roundabout, that is also circular motion. Not only that, but we can also talk about the moon rotating, moving around, orbiting around the Earth. That also refers to what? To circular motion. Okay. So why is circular motion so important? Why do we have to talk about it? Okay. So when we get to study most of the things in our lives, we understand that it is actually not possible to do away without it. Okay, we cannot do anything without circular motion. Most of the things that we do are very dependent on the same idea of what? Circular motion. Today, according to the SpaceX, we are told that there are over 600 satellite dishes on the moon, okay, in space. They say, so we have over 600 satellite dishes. They all use idea of circular motion because without them, we would not be able to watch our television using our satellite dishes that we have at our homes. So these are all dependent on the idea of circular motion because they move the orbit around the Earth. That's why we are able to have network. That's why we're able to watch our televisions. Okay, so even just a roundabout it's very important as well. Okay, so these have got different applications. So as we talk about circular motion, we need to do some calculations in relation to kinematics. So just from our translational motion, where we've talked about velocity, we've talked about displacement, we've talked about distance, we've talked about the time it takes, we've talked about acceleration, we've talked about different concepts. We're able to draw graphs. So the same applies to rotational motion. Just like we have velocity, we also have what we call angular velocity under rotational motion. So we'll be able to identify and be able to connect the relationship that lies between the rotational motion and the translational motion or the straight line motion that we all know about. Okay, so just like we know for something to move in a straight line, it needs a force. So for a car that is static, it needs a certain force to be applied for it to move in a certain direction. All right. So there will be a force that is supposed to be applied on an object for it to move in a straight line. So the same applies to what? The same applies to a rotation motion. So for something to move, there's need of what? There's need of a force. Okay. So for these objects to be moving in a circular motion, there is need that, let me just draw this so that you're able to see properly. So you have a circle like this. So you have something moving in a circle, right? So let's say, for instance, maybe you're talking of a ball. It's moving around the circle. You've tied it to a string, then you're rotating it in a circular path. So you find that this will continue moving. It will continue what? Yeah. So let's say you've tied, this is a string. This is a string that you've tied to a ball. Then you're rotating it. Let's say maybe in a horizontal path. You're rotating it. So it's possible that this ball can go away, right? It cannot continue moving in circular motion. It's possible it can go away in a certain direction. But because there is a force that is acting along the chord of a string, this ball continue moving what? Moving in the circle. All right. But if the force that is pulling it towards the center or towards that circular path, if it becomes too small, the ball may go away. All right. You can try that. Try to use a lot of energy, then try to rotate something that you've tied on a string. Rotate it very fast. Then you try to loosen you just let go of the string. You find that the ball will go away. It will move out of the what? The circular path. So this ball, if you're rotating it, continue rotating it very fast. Rotate it, then let go of the string. You find that this ball may even go maybe in that direction. Okay, it may go in that direction. So what are we trying to say? So we are trying to say if a ball or anything is to continue moving in a circular path, there is need of this force that is very important. So the force that pulls something or that makes something to continue moving in a circular motion or rotational motion is what we call what? Centripetal force. So centripetal force is the force that makes it possible for something to move in a circle or for something to rotate. It's very important. All right. So the centripetal force is actually given by the product of mass by the linear velocity squared, okay, divided by what? Divided by the radius. Very important. So what is the force that makes something to rotate in a circular motion? Okay. So are there any questions? Are there any questions? Okay, so just assure me that you're online. I'm not disconnected or you're not disconnected. Just say something so that I know I'm still connected to the internet. Hello, are we together? Okay, so we've talked about that. Another key concept that you need to understand. Okay, this is going to be a conceptual question. I'm going to ask you guys. So if you have something moving around the circle, I want uh, each one of you to say something. So what can you say about the velocity? Does the velocity change or well, okay, what can you say about the velocity and the speed? Does the velocity change or it remains the same as something is moving? Let's say this ball is moving at the same speed. Okay, you are rotating it at the same speed. What can you say about the velocity? Is the velocity the same or it's not the same? What can you say about that? Okay, so I've not said you increase the force. I've said you just rotate it. You continue rotating it with the same. Okay, I'm not asking about the speed. I've said the speed. Okay, let's say the speed is the same. Okay, you are rotating it at 20 meters per second, for instance. Fact, that is not true. You can't rotate it. Let's say you're rotating it at 20 radians per second. So, do you expect the velocity to be the same as well, or what can you say about the velocity of something that is rotating? Okay. What do others say? What are others say? Oh, so you're all saying it will be the same? Okay, but may I have first somebody to define for me velocity? Okay, a different formula or a different explanation, but will not use displacement. How can we define velocity? So I don't want the class to be boring. I'm asking you guys, what is velocity? Okay, you are right, you said it is the rate of change of displacement, but I'm asking of a different explanation that won't use displacement or use speed in your explanation. Okay, you're all quiet. All right, so learn to speak out. The more you speak out, the more you be able to understand. So what are we trying to say? Velocity. Pardon? Okay. Yeah, that is true. That is also in relation to displacement. Okay, so we can define velocity to be the rate of change of displacement, as you said, but I wanted the definition that had to do with speed or direction. So velocity is speed with direction. Okay, it needs a direction. All right. So let me let me illustrate what I'm saying. All right. So if you have got, for instance, a car going this way, so if it's moving at 20 meters per second in this direction, what is this velocity? But if a car was to like make a turn and begin going this way with the same speed, we are going to call it's going to become negative 20 because of what? The direction. But the speed will still be 20 meters per second. So what I'm trying to stress out is a fact that velocity needs or it is depends on the direction. All right? Depends on the direction. It is a speed with direction. So if we are saying the ball is rotating along a circular path with constant speed, we don't expect velocity to be the same. Why? Because as something is rotating, it is changing directions at each position. Okay? Something in a circle changes direction at each point. So just like you can say, this ball is like going this way. When it reaches this point, it will change the direction. This point, it will continue changing directions at each point. So therefore, velocity of something in rotational motion is not constant. It changes from point to point. Whether you are told it was rotating constantly or at a constant speed or angular velocity, just know that velocity changes. All right? Velocity continues changing. So that's the point that I wanted to let you know. All right. Away from that, I want to remind you as well that just like we are told that the centripetal force, this formula is important. So centripetal force is actually equal to what? Mv squared over what? Over the radius. So this formula tells us a force, okay? It has given us a force. So generally we know that the force is given by the product of mass and what? Mass and acceleration. Okay. So now let's say this is our centripetal force. So if we equate it to mv squared over our radius to be equal to the product of our mass and acceleration. So you're going to see that your mass is going to be what? Your mass is going to be common. So in short, if you make A to be the subject, you find that A is going to be V squared over what? Over R. Okay. So this is another formula that is very important. This formula represents what we call centripetal acceleration. Okay. So if you want to calculate the rate of change of velocity in a circular path, you use this formula. So this part of this formula, this part V squared over R, represents what? Centripetal acceleration. Very important. Okay. In addition to that, we say that centripetal forces are different depending on what you're talking about, right? So if we talk about a car that is moving around or moving uh, at a roundabout, actually, yeah, when it is rotating, the tires actually are the ones that are rotating. So in such a case, what is a centripetal force? What will make sure the car doesn't like go out of the circular path? Okay, what is going to guarantee that the car is going to rotate? So there is what we call friction. Of course, you know what friction is all about. So friction is the centripetal force when something is for a car, right? When a car is moving along a circular path, what acts as a centripetal force, what makes sure that the car is moving along the circular path is what we call friction, okay? So friction is given by the product of the friction, what? Coefficient multiplied by the normal force. And for something that is on a level ground, the normal force is what? Is just a weight, which is mg. So this is equal to your friction. Okay. So very important. Okay. So in such a case, you may be asked questions like calculate the minimum speed that a car must rotate so that it remains in what? In the circular path. So there is what we call these interconversions between the centripetal forces. All you have to do when you're asked for one, when they ask for one of these things for you to calculate, all you have to do is identify the type of centripetal force, then equate the general formula for the centripetal force to the one that you are given. So in case you're given a car that is moving, okay, let me just give you an example. Let's say you have a car that is moving along so a car was coming from this way. It is a roundabout, okay? then the car begins to rotate this way. All right. So then you're asked, then you're told the car was moving at 20 meters per second, for instance. Okay, along this path. So then they ask you to say find. Then you also, of course, they're supposed to give you maybe sometimes they may not even give you the mass. Of course, they may not give you the mass. So you are given the velocity of the car as it is moving along the roundabout. Then they ask you to find the coefficient of friction. That is the minimum coefficient of friction required to make sure that the car will continue moving what? Along the roundabout. How do you calculate that? So first of all, like I said, you're supposed to identify the type of centripetal force that is involved in that rotational motion. So when a car is moving around the roundabout, we say that it's the friction that is supposed to provide the centripetal force, because we said a centripetal force is very essential to make sure that something moves along what? The roundabout. So because if there was no centripetal force, or if there was no friction, this car may not rotate. It may end up going this way. All right? But because there's friction, there's a minimum friction required for it to rotate. Okay? So what do we do? So we've identified the type of centripetal force, which is friction, and we know that friction is given by what? Friction is given by the coefficient of friction multiplied by mass and gravity. Then we know that the general formula for centripetal force is what? Is given to be mv squared over what? Over r. Okay. So I forgot to give you one of the concepts. You're supposed to be given the radius of the roundabout. So for instance, you are told it's 10 meters. Okay. So you're supposed to equate the two formulas. So get the first one. Mu s mg should be equal to mv squared over what? Over the radius. Okay. So the mass is not actually important because it's common on both sides. Okay. So for you to find your coefficient of friction, you're supposed to divide by gravity. So v squared over r multiplied by what? Gravity. So for you to find your answer, you just have to say 20 squared divided by 20 multiplied by 10. Okay? So that's what I wanted to stress out. That's what I wanted you to know. So very important as well. Very, very important. Okay? So just interconnect concepts. Understand, identify the centripetal force involved. We'll look at some examples during the story session, but that's just actually the foundation of centripetal force. So in cases where given the moon rotating around the earth, we say that the centripetal force that makes sure that the moon is actually moving around the earth or orbiting around the earth is the pull of gravity, and the force is given by the product of it's given by g constant multiplied by the mass of the moon multiplied by the mass of the earth divided by what? Divided by the radius. Should be the radius squared. Okay, so this formula is very important as well. This one gives us a centripetal force for the moon orbiting around the earth. Okay, so g is a constant that you always be given. Then the masses you're also supposed to be given. Then they'll give you the radius as well. So you'll be able to equate the two. So you're supposed to equate this one according to mv squared over what? Over r as well. In cases where they ask you to find the velocity or any other measurements, it can be the mass, it can be the radius, you just have to equate the two. Okay. Then in cases where you're given for instance, an example where I gave you where you've tied something to a cord, okay? Okay, where something is tied to a cord, then or a string, then this is moving around, there is rotational motion involved. So in such a case, what provides the centripetal force is the tension. Okay, so a tension is just a force, and depending on what you're talking about, tension will be identified. Okay, you'll be able to see the tension. So in cases where you're given, there are times when there is this support, then you've tied, for instance, maybe a ball on the end there. Then you will try to push the ball so that it begins to rotate. You find that the ball is going to rotate in a horizontal circle, something like this. Okay. So what is acting along the rope is the tension. Okay, but what is providing the centripetal force is actually the x component of what? Of the force. So you find that the center of a circle is somewhere in between here. Okay. Then this tension is actually going to be divided in two components. There's a y component of the tension, then there's also the x component. But if you try to look at the circle that is being formed, you find that what is pushing it towards the center is this component of that tension. So assuming that is the angle that you are given, for us to find this component, what are we supposed to do? So it is actually the opposite. So we'll say sine theta opposite, which is the centripetal force in this case, divided by the hypotenuse, which is the tension itself. So in such a case, the centripetal force is supposed to be given by tension multiplied by what? Sine of the angle. So I'll look at examples as well. So what I'm just trying to tell you is that whenever you're given a question to do with centripetal force, identify the type of a force that is involved. Right. We talked about all this. I'm just trying to do a recap so that you are not left out behind in case you missed or it has been over a week, so most of you have forgotten. Okay. So any questions concerning the centripetal forces? Are there any questions? Any questions? Pardon? Or about tension? You'll be able to identify what's going on. Like they tell you something is okay, whenever it's a cord that is involved, or whenever it is a string that is involved, something is tied to a support, it is tension. Tied moving in circular motion. Give an example. Yeah, that's what I was saying. Something is tied when it begins rotating in a circular motion. That is tension. Is it not what? Yeah. So now you are confused. Anyone who can explain what I said about centripetal force and tension? Centripetal force is what? Anyone to define centripetal force? No one is able to define centripetal force. What is the centripetal force? Guys. After no one has understood what centripetal force is. Anyone to give an explanation? What is the centripetal force? Yeah, zero work done. Okay. All right. Okay. Pay attention. Don't be too serious when you're reading. So just be paise, you'll be able to understand. So rotational motion, something is supposed to move around a circular path. So I said for it to move around a circular path, there is a force that pulls it towards the center. So what force that makes sure that something will continue moving around a circular path is what we are calling what? The centripetal force. So this is what I'm saying. For something to move around a circle, for instance, this ball, if it is to continue moving around the circular path, there is supposed to be a force putting it towards the center so that it doesn't go out of the path. Because I was giving an example of you rotating something that you've tied. You've tied a bulb on the string. Then as you continue rotating it, it will continue moving along that circular path. But when you let go of a string, it will go away. It may go in any direction. It may go that way. Okay. But why I want it to continue rotating along one circular path is because the centripetal force that you were providing, you've stopped providing. Okay. So you were asking a question, therefore you were asking me a question to say, sir, what about if you, is it not a so I said this centripetal force is a general thing. It is just standing in for a force that may provide that force. So tension is an example of a centripetal force. So you are just, they are not different. Tension is one of the examples of a centripetal force when you're talking of something tied to a string. But when you are talking about of a car on the roundabout, it is actually friction that is the centripetal force in such a case. If you're talking of a moon orbiting around the earth, you're talking of gravity being the centripetal force. Okay? So centripetal force can be any force providing what? Or but a force that is making sure that something continues moving or orbiting in a circular path. Does that make sense? Or we are still not understanding? Hello? Hello, are we together? Anyone who has understood, please, to just say something. We have Catherine, we have Hope, Louis. Anything to say? To just assure me you've gotten it, or if you have a question, just ask. But just being quiet. Just come again. About what? Okay. All right. What can others say? Okay, so I'm just trying to find the diagram that I'll use to explain. All right. Yeah, I'm just trying to find. I've actually found it. Let me just now try to explain more. Okay, so let me know when you're able to see the screen.
Yeah, we're able to see it.
But we've understood the definition for a centripetal force, right? It is something trying to make it, it's a force trying to make sure that something continues moving in a circular path. Okay, so I hope this diagram will make us understand. So able to see, let's say you have a string, like, okay? Able to see the cursor moving. Hello?
Yes, sir.
So you've tied a bow to a string.
Yes, sir.
Then you begin rotating it on top of your head. Okay. So there is a force that is acting along the string, this string. There's a rope acting along that string that is making sure that the bow continues what? Moving in that circular path. Okay. So let's imagine the string maybe breaks or it cuts. What do we expect? Is the bow going to continue moving in that circular path, or what is going to happen? Where is it going to go? Okay, so let's say the bow is somewhere here. What do we expect when the string cuts? It may go that way, right? For instance, this point where it's labeled A. Okay, let's say if the string cuts, this ball may what? May go in that direction. It will not move in the circular path. So now what are we trying to say? We're trying to say that for circular motion to be in existence, or for circular motion, or for a rotation or a rotation to occur, there is need for what is being called what? A centripetal what? Force. Are we together?
Yes, sir.
So now in this case where you've tied something like that, what is acting as a centripetal force is what? The tension. And what is the tension? Tension is the force that acts along a string, a cord, or a rope. It is just a force. So tension, let not tension confuse you. Tension is just a force. A force acting along a rope or a cord or a string if you want to. Okay. So now imagine where you are holding the string. That is now the center of the earth. And let the ball now be the moon. So now what is going to make sure that the moon doesn't go away in the space, but it will continue? And what makes sure that the moon continues rotating around or orbiting around the earth? It is what? It is now gravity. Gravity is going to make sure that the moon doesn't go away. That's why the moon has been rotating or orbiting around the earth for billion of years, okay, because of gravity. So in that case, gravity becomes our centripetal force. Okay, are we together? Are we together? Hello? Or we are confused again on gravity? Hello? Hello? We don't have enough time. Please just communicate if you understood. Pardon?
We've understood.
Okay. So just when we are done, get questions, try to attempt them. If you have challenges, share them to the group. We'll be there to help you. If you learn a concept and you just like go mute, just okay, I've learned, you pack your books, you'll be disappointed next time we have a class again. You forget. Because we talked about this the other time and people said we've understood. Okay, so I want to reintroduce again the connection that is there between this. I think that's where we're going to end. Yeah, the connection that is there between the centripetal, or let me say circular motion, and the translational motion in terms of the formulas. So in translational motion, where we can denote displacement to be x, it can be s, others may use d for distance, all right? Velocity v, acceleration a, mass m, momentum to be p, and force to be f. Okay. So now, if I ask you a question, what is the rotational counterpart of displacement? What do we call it under circular motion? What do we call displacement when we are under rotational motion? We talked about these terms the other time. So if you're talking
Theta.
pardon?
Theta.
I'm not asking of a symbol. I'm asking of the name. Yes, it is noted by theta, but what's the name? Okay, so something moving in a straight line, we are saying is displacement. Something moving or something in rotational motion, we are calling it now angular displacement. As simple as that is. Denoted by the dots, theta, like she said, but theta for an angle. How about velocity? What do we call it under rotational motion? Denoted by so
W.
okay, it's not really W, but so it's omega. Okay, you're right. Then acceleration. Acceleration. What is it called?
Alpha.
Angular acceleration. Denoted by alpha. Momentum. We didn't talk about that. But of course it become angular momentum. Force is not angular force. It's torque.
Angular acceleration.
Pardon? It's not angular force, it's angular, it's torque. We'll get to talk about that after we are done with the basic rotational motion tomorrow. So this is the definition now. Okay. Okay, so let me get to the board. Are you able to see the board? Okay. Are you able to see the board?
Yes.
Okay, so now we are trying to connect now. Don't mind us, we don't know how to draw. We're very good at not drawing. So when you have something like this in a circular path, right? A ball, for instance, rotating, and this is the center of the circle. This is the radius. So something moving in rotational motion has got both, it has got both of these. For instance, if velocity, it has got velocity as well as the angular velocity. Get me clear on that point. Okay? Something moving in rotational motion, we can talk about it in terms of linear motion as well as what? Rotational motion. What am I trying to say? I'm trying to say, okay, so let's say this ball has moved from this point A to this point B. Are we together? Are you getting me?
Yes.
So now there is what we call the arc length. Okay, the length of what? The arc. So that the length of the arc is that is the displacement, or that is the distance. It's like now the string, you make it what? You make it. If you were to get to cut, maybe let's say you've made a circle using a rope, then you cut that point and this point. If you come and hold this in a straight line, okay, so that it comes out in a straight way. Okay, somebody holds point A and somebody holds point B. So this is what we are calling the arc length. This is S, denoted by S. So that stands for now what? Displacement, which is in translation or straight line motion or linear motion, if you want to. Okay. Now that is not rotation. Rotation, what are we interested in? We said for displacement in rotation, what are we interested in? We said angular what? We said angular what? What is the counterpart of displacement in angular motion or rotational motion? Or we have forgotten now again. What is the counterpart of displacement? Angular what? Angular what?
Angular velocity.
Is a counterpart of what?
Displacement.
But how? How come? Why are you combining them? So displacement. I don't know if maybe you're not understanding displacement. Displacement is distance, guys. Displacement is distance. So the actual counterpart in rotational motion is angular displacement. It is not changing. We're just adding the word angular so that we refer to something moving in a circular path. Okay? So now this is what we are calling now your alpha or your theta. Okay? Okay. So I want you to understand that the arc length AB has got a relationship compared to the angle inside there. Okay? So the angle talks about the angular displacement, talking about the rotational motion. The S there, or the length of the arc AB, talks about linear motion. All right? So there is a relationship that lies between the two. And what relationship is there? The relationship that is there is that the length of the arc AB, which we are saying is S, is actually equal to the product of the radius of the circle by theta. Understand that. Okay? It's that simple. It's very simple, very simple. Understand that. Okay? Are we together? Okay. So from the formula that I'm from writing there, if you make theta to be the subject, you divide by the radius on both sides, it will now be the arc length divided by the radius. So implying that if you are given the arc of a length, the length of an arc, if you divide by the radius, you're able to get what? The angular displacement, or theta in other terms. Okay? And this angle that we deal with is always is going to be measured in radians. Okay? Okay. So it is all hand displacement, the angular displacement. We're trying to demonstrate that. Okay. Now, for us to understand now what this is all about. Okay, so what is the angular position theta if we go around the circle 2 times? Okay. Okay. So I want you to know that the total length of the arc length of the circle, or the total angle. Okay, let me ask you in terms of the degrees. How many degrees makes up the whole circle?
Yeah.
Okay, so in radians, how many radians make up a full circle, or a full evolution, or one rotation? You guys have done mathematics, you've done trigonometry. 360 is equal to how many radians? You have your coordinate system here. Moving from this point to that point, it's 180 degrees. It's equal to how many radians? Pi radians. So if you are to make a full evolution, making a full circle, it's 2 pi. So if you didn't know, or if you've not done trigonometry, I want you to know that 360 degrees is equal to 2 pi what? 2 pi radians. Alright? 360 degrees is equal to 2 pi radians. Okay? That's the concept that you need to know. Okay. So now if you're asking you, it has gone around how many times? 2 times. It is going to be how many? It's going to be by 2, of course. All right. That is in terms of the angular what? In terms of the angular displacement now. You're just trying to convert now to angular displacement. So the theta, when something has moved around twice or just once, it's 2 pi. Now if it has moved twice, it will be 2 pi multiplied by 2, which is now going to make 4 pi. Okay? Now, I want you to know, that was in terms of the theta, the angle. But for the arc length, okay? So now, if you move from this point, you rotate until you get to this point again. The arc length S is going to be equal to 2 pi r. That is the arc length. But the theta inside that you've covered, all this is 2 pi. Okay? But the length of the arc is 2 pi r. Okay? So don't be confused on such simple concepts. Okay, so let me just finish up velocity. So we say that somebody was saying W velocity, if you go to rotational motion, it is called now angular velocity. Okay, so angular velocity is just given by the change in displacement, the angular displacement by the change in time. All right, that's what you're going to be taught. Okay. So what are we trying to say? So we are trying to say, given a circle, then given that this ball moved from this point to this point, okay, and it covered this, for instance, it covered maybe pi over, remember we're using radians here, pi over 3 radians. This is actually equal to 16 degrees. So then you asked, when it took about, for instance, 6 seconds, then they ask you to find what? The angular velocity. So angular velocity, which is denoted by W, is given by the change in what? The change in angular displacement divided by the change in time. Okay? So just like we know in translational motion, velocity is displacement over time or distance over time if you want to. So even here we are going to use the displacement or the distance. Here it's called angular displacement and we refer to theta divided by the time. So it covered pi over 3 divided by what? Divided by 6. So if you are to divide this, what you're going to get is going to be what? Your angular velocity. And the units for your angular velocity are radians per what? Per second. So the angle theta, the units are radians. So yeah, that's what you need to know, you guys. Very important as well. So to just end our lecture, for angular acceleration. So we know our acceleration. Okay, just going back to the angular velocity. Just like we said that S, the displacement, is equal to radius multiplied by the angular displacement. So our linear velocity is also equal to radius multiplied by angular velocity. So our acceleration is also equal to radius multiplied by angular acceleration. So angular acceleration, just like we know, acceleration is final velocity minus what? Initial velocity divided by what? Divided by time. So even angular acceleration is omega final, which is angular velocity final minus initial divided by the time. So these concepts, guys, are not different. The concepts are the same. All right? Don't just think rotational motion is difficult. Don't panic. Just take it easy. Try to research, try to find questions, try to attempt them. Try to see the conversions between the angles. Then to just end this, if you look at the formulas that we have and linear motion, you have this formula, for instance. So what is your counterpart of velocity under angular motion? It's what? Angular velocity. So this is angular velocity final, angular velocity initial. Then acceleration is what? It's angular acceleration, which is denoted by alpha by time. So all the other equations can be converted to rotational motion by just putting the counterparts. Are there any questions before we end? I'll share the notes to the group so that you can check them out. Are there any questions? Or have we understood? Or are we confused? Okay, so one person has understood.